For the next couple problems that are in this problem set for number bases part 2, I decided to cut the video in half so it wouldn't be too long. So if we look at problem 4, we have the number y represents one of the digits in base 15. So when we see base 15, whenever we have bases that are bigger than base 10, we start often using letters for the remaining digits. Okay, so we're in base 15, and when this number 6y82 is divided by 7, the remainder is 1. Now, before we think about this and how to approach it, whenever you see the word remainder, you want to be thinking about how can you do modulus division. Okay, we want to be doing modulus division. So I'm going to start by expanding this expression out, okay? And I have a note here that I wanted to have written so that I didn't forget to mention it. When we are working with remainders, you want to think about the modulus arithmetic. So any value can be replaced with its equivalent, mod 7, when doing multiplication, addition, and subtraction. Things are a little bit more complicated with other operations, but for those three, we can do a direct replacement. Just like how if you were to have had like 10/6, you could just replace it with 5/3. It's that simple and common of a replacement. So let's first begin by dividing this out, and then we can go ahead and look at how we can do some replacements for us. So I'm in base 15. I have 4 places, which means my leftmost digit will be 15 to the third. So I'm going to write 6 times 15 to the third plus y times 15 squared plus 8 times 15 plus 2 times 1. And then when I take this expression and when I divide it by 7, so I'm going to put mod 7, all right? And when I do that, that equals 1. So another way that you might see this written is you might see it written with this notation here where we have like the 3 lines, which is another way of just saying equivalent to. All right, so I'm trying to take all of this and I'm trying to mod it by 7. And when I mod it by 7, it's going to be equivalent to 1. So let's first look and think about, well, what can I replace? Well, any number that is smaller than 7 when you mod 7 is the same value. So we really only need to seek out values that are greater than 7, so 7 or greater. So we've got the 15, and then we have the 8. Those are the values in my problem right now that happen to be greater, that are 7 or greater. All right, so let's think about this. If I were to do 15 mod 7, that would be equal to 1. So that means everywhere I see a 15, I can replace it with 1. If I were to do 8 mod 7, that's also equal to 1. So right now I have 6 times 1 plus y times 1 plus 1 times 1 plus 2, and that's equivalent to 1. Okay, so let's clean this up a little bit. We have 6 plus 1 plus 2, so that's going to give me 9. So I have y plus 9 equivalent to 1. And then again, hey, what do you know? I have another value that is 7 or greater, so I can simplify that with modulus. So 9 mod 7 equals 2. So now I have y plus 2 is equivalent to 1. And if we solve for y, we get y equals -1. Now, we're looking for my, my possible values of y that can make this true. And recall that y is a digit in base 15, meaning it's from 0 to 9 in A through E. So what we're going to be looking at here is we're going to say, okay, how could I get those possible values? So just like here, how we reduced with modulus, we can also find greater values by thinking in the other way. So what we can do is we can add 7 repeatedly to get equivalent answers. So if I were to add 7, that would give me 6. If I were to add 7 again, that would give me 13. And when you're trying to figure out, well, what exactly is 13? If we think about it, A is 10, B is 11, C is 12, so D is 13. So my answers here for Y are 6 and D. All right, so this next problem deals with the factorial base system. And this base system is denoted with a little exclamation point for the base. And the way that this is described is that the kth digit from the right has a place value of k factorial. So when we look at this expansion here, we can see 1 factorial, 2 factorial, 3 factorial. And that is how they expand it out, okay? Now, in terms of how some restrictions that we have here, so just like how in a problem, let's see, like we had up here, where I said that we weren't able to have any values that were greater than that base because of the base that we were in. That same rule applies here, but it's just a little bit different. So here, the digit with the place value of k factorial can only take on values between 0 and k inclusive, meaning that that value is included. So if I were looking at something where I had 1 factorial and 2 factorial and 3 factorial and 4 factorial, what that's basically saying is that in this ones place, I can only have values from 0 to 1. Here, I can only have values from 0 to 2, from 0 to 3, from 0 to 4, and so on. Okay, so now that we know how this base system works, let's go ahead and do the actual problem. So we are supposed to figure out how to write this value 9001 in the factorial base system. Now, similarly to how we did our first problem with the 11s, where we wrote out the powers of 11, we're going to do the same idea, but here we're going to make out a chart of factorials. So, and you might not sure how far we're going to have to go. Basically, we're looking for the largest factorial that can go into 9001 without going over. So our factorials are going to be 1, 2, 6, 24, 120, 720, 5040, and looks like we can't go any further because that would go over. So 7 is our greatest. Okay, so now what does that tell me? That tells me that my last digit is going to be the kth digit, so that means my answer is going to have 7 place values. So I can start out with 1, 2, 3, 4, 5, 6, 7, and this is my 7 factorial all the way down to my 1 factorial. Okay, so I want to ask myself, how many times can this value go into 9001? And it can only go in one time. So I have 9001, and I'm going to subtract 5040, and that will give me 3961. So one in one time. All right, now I am down to the next value, 720. How many times can I put 720 in here? Well, I can do it 5 times. So I'm going to subtract off 720 times 5, which is 3600. And that leaves me with 361. So how many times can I put 120 in 361? And I can do that 3 times. So I'm going to subtract off 360, give me with 1. And that means it only goes down over here with 1. I have no 24s, no 6s, and no 2s. So my final answer is 1530001 in the factorial base. All right. For this last problem, what we need to do is we want to find the sum of all base 10 values.